Hi everyone, this is Mrs. Musoff. And the last piece we're going to talk about today is defining absolute value equations as piecewise functions. We're also going to graph them a little bit. Now, your homework has some regular piecewise functions to graph. Remember, to do those, you just need to come up with a table of points, and make sure that you get enough points to truly see the shape of your graph. Okay, but when it comes to defining absolute value equations as piecewise functions, that's going to be really important when you get to calculus, so might as well practice a little bit of it now. All right. So remember, an absolute value function, this is what our graph looks like. It's one of our 10 parent functions that we should already know what they look like, and we should be able to come up with points. But the important part of today is being able to recognize that this graph is really just two separate lines kind of spliced together, and that's why we can write it as a piecewise equation. So if we look at just the right side of this graph, that's just the line y equals x, but that's only true for x greater than or equal to 0. So that's our first piece. If I want to define the left side of this graph, it's just the opposite of what's inside that absolute value, so it's negative x, and that's for x values less than 0. All right. Using that definition, we can actually then make the claim that no matter what is inside of the absolute value, you can always rewrite it as the piecewise function where the inside of that absolute value is your first piece, and the exact opposite of what's inside is your second piece. And then to figure out kind of that boundary line, you just take that inside piece, whatever's inside the absolute value, in this example like x minus h, and you set it greater than or equal to 0, and you would solve. And that's how you can figure out that boundary. All right. This equation up top here, it's that general form equation for absolute values, and that's what we can use to kind of help us graph it, because if it's in this format, we know that the vertex is h comma k, and you can actually use this number a as your slope in order to get both of your two lines to turn it into a v. All right, let's take a look at an example. So it says given the equation, graph it, then write it as a piecewise defined function. And our equation is f of x equals the absolute value of 2x plus 5. So to start, in order to graph it, we're going to need to know where that vertex is. And then once we know the vertex, the shortcut way to graph these, you certainly can use transformations, but the shortcut way to graph absolute value functions, since we know it's just going to be a line going in both directions from the vertex, you can actually use that a value that we were talking about over here as your slope. And just as long as you remember to go like the positive and the negative direction, you'll end up with those two lines that will form your v. All right. So to help show you what that would look like here, if I wanted to find my vertex, remember h comma k, that's the number you're adding or subtracting to x, and then the number you're adding or subtracting on the outside. Make sure you're doing opposite of the one inside, same as the one outside. But in this problem, we have this little problem where there's a 2 here, and we can't really have that. So what we do in order to really isolate that left or right shift is we factor that 2 out. And because it's an absolute value, the absolute value of 2 is just 2, so I can actually pull that 2 completely out, and that 2 becomes my a value. Right, and so based on this equation, now I can find my vertex. It's the opposite of this number, right? This is a left shift, so that'd be negative. And then it's the same as this number you're adding out here, which there is none, so I wouldn't have an up or down shift, so that'd be 0. So my vertex would be negative 5/2 comma 0. And my a value that I'm going to use for my slope is going to be 2. And so I would plot my vertex, and then I would go up 2 over 1, and that's how I can get this graph. All right, just so you can see it, that's the up 2 over 1 that I was talking about. You just have to go in both directions, and that's what can form those lines. All right. Now, writing it as a piecewise defined function is a little trickier, but we're really going to use this definition down here to help us with it. It says no matter what's inside the absolute value, you'll have two pieces. One is exactly what's inside, and one is the exact opposite. And to find your boundary value, you're just going to take what's inside and set it greater than or equal to 0. So if we did that for this problem, I have two pieces. One is exactly identical to what's inside the absolute value. One's the exact opposite. And then I just need to set that inside part greater than or equal to 0 and solve, and that will find me my boundary values. Now, when I solve that, what you'll notice is that boundary value is actually just the x-coordinate of my vertex. All right, so you could have even used this original piece in order to help you with it. You'll end up with the same equations here, and you'd end up with the same values. So it doesn't really matter if you use this factor version or if you use the original. All right, so then this would be my piecewise definition. Again, I know it's kind of tricky when I'm not actively writing these down, but hopefully you're still able to get a lot out of it. If you have questions, make sure you're using your group members and asking them first. But then obviously if you guys are stuck on anything, just circle them and I'll be happy to answer your questions when I get back. All right, thanks for watching and listening. See you soon.